constructions. Okay, and you guys hear me? I'm unmuted, right?
Yep.
Okay. Snaith constructions on Wilson spaces. And this is a project joint with Alan Yuan, who's here, and Jeremy Hahn. So Snaith constructed complex K theory from CP infinity by doing what I'm going to call a Snaith construction. So he says that complex K theory is equivalent to the spectrum that you get when you take the pointed suspension spectrum of CP infinity and you invert a class X, a generator of pi 2 of CP infinity. Now, CP infinity is an infinite loop space. So the suspension spectrum, suspension infinity plus of CP infinity, is an E infinity ring. And you can localize E infinity rings and still get an E infinity ring. And so this right-hand side comes with an E infinity ring structure. Of course, KU itself has a standard E infinity ring structure, and the equivalence can be made E infinity. So Snaith also showed that MUP equivalent to suspension infinity plus of BU with the degree 2 class inverted. But my co-authors, Alan and Jeremy, and Yuan, say this equivalence can be made E2, they know, and they know it can't be more than E infinity, than E5. And of course, Alan can correct me since he's here. So this can't be E5. So in fact, MUP has a standard E infinity structure on it. The right-hand side has a standard E infinity, or has an E infinity structure that comes from the infinite loop structure on BU, and they're actually just different. In fact, BU has 2 different E infinity structures. Presumably, neither of them are the same as the one on MUP. So this gives you 3 different E infinity structures on MUP, if you like. Anyway, so we were interested in generalizing the structure, this. Like, why did this work in both cases, or well, in some sense, work in both cases to generate interesting spectra, sometimes with the same E infinity structure we're used to on them, sometimes with different structure. But so several other generalizations exist. So Jacob Lurie in elliptic cohomology 2 constructs E theory via arguably a Snaith construction. I mean, he inverts a class like this. And Westerland has a paper which is quite related to our work called Higher Chromatic Analog of Image of J. So these are two prior works that generalize this in some sense, but these are both in the K and local category. Which makes sense because, you know, in this case, K theory is an integral, or, you know, I mean, you can construct it as an integral spectrum. KU, complex K theory, you can construct as an integral spectrum. But if you're going to try to construct like a higher height analog of it, like, you know, higher height Morava E theory is a related spectrum. These are all intrinsically K and local things. And so you might think to just start out by working in the K and local category because you're not going to get something integral. So we want to consider P local spectra. So throughout the talk, I really mean my spectra to be P local implicitly most of the time. And so the question is, what can we replace? You know, what do CB infinity and BU have in common? You know, they're both very nice, you know, infinite loop spaces. And so we say, like, okay, we're going to replace them with a general Wilson space, right? So let's start a definition since this is very quick. You know, a Wilson space. Let me see if I can write an italic. It's just a space with even and torsion-free homotopy and homology. So, right, that includes both CP infinity and BU. You know, and then there's the BSU, BU6. You can take some like BO with 2 inverted, B spin with 2 inverted. And you know, generally you get these as loop spaces of BPNs. Okay, so we're gonna, instead of you know, say CP infinity or BU, just plug in a general Wilson space and plug in just some element of the homotopy. And so here's what we say. One thing we say. So this is me and Jeremy and Alan. Suppose that just W is any Wilson space. And X in pi star of W is a non-zero class. So I'm going to think about W as an E infinity space. Wilson proved that every Wilson space has at least one E infinity structure. So just implicitly, I'm picking an E infinity structure on it. And so in this case, so now suspension infinity plus of W with X inverted is E infinity ring with its E infinity structure determined by the infinite loop structure I picked on W. And it has torsion free and even homotopy. So it's complex oriented. And it's also Lamb-Weber flat. So this construction works quite generally. And so, but we're also interested in trying to relate these things to, you know, E theories, right? So in the case where we put in CP infinity, we go on P local KU. Well, I guess now I'm thinking about W is a p local spectrum. Most Wilson spaces only exist p locally. Right, but we're not going to get a higher height E theory out of this directly, as I said, because you know, it's not giving us K and local stuff. In fact, these spectra are giving us, you know, E infinity rings that have no, they're no Ethereum. They don't have any completions in them, which is, I think, kind of cool. But yeah, not E theory. So, okay, so first we just investigate the additive structure of the K and localizations. So, you know, if it's going to orient an E theory, it better have a non-trivial K and localization in that, you know, for that n, for the height of the E theory you're trying to orient. So I guess I should abbreviate this suspension infinity plus at W of X inverse soon. So the K and localization of this is equivalent to the K and localization of a wedge of Johnson-Wilson theories of height n. And so this is Johnson-Wilson theory here. This wedge could be empty on the right-hand side if it's just 0 in that degree. So the first question, you know, assuming we know this, is, you know, when is the K and localization 0? So for what n is the K and localization of, I'm just going to call this thing R, non-zero. Of course, this is going to depend on W in the class X. So I'm going to specialize in a moment to some particular interesting cases. So for a typical case, if you just pick like a random W and a random X, you get something of infinite height. So you get something sort of like MUP, where none of the K and localizations ever vanish. But for particular cases, we get things like where we put in CP infinity and we inverted the degree 2 class, we got KU out, and the K2 localization of KU vanishes. Right. So Jeremy says that if I have an E infinity ring, it has some height H, which is, you know, a natural number in or infinity, such that if n is less than H, the K and localization of R is non-zero. And if it's greater than R, say less than or equal to, if n is greater than H, then the K and localization of R equals 0. So in those words, what is the height? Okay, I guess I need a new page. Okay, so now we're gonna specialize to a particular set of rings. So let's let. Okay, so now I'm just gonna write down a particular Wilson space. So we have this notation V of n, which I don't think is, this is fairly standard in the Wilson spaces. Works. And so W H minus 1 is going to be this particular Wilson space. So as I said earlier, that they're all loop spaces of BP related spaces. So this is a Wilson space. This BP H minus 1 is BP mod some choice of VH plus 1, etc. And, you know, of course, these ideals like P, V1, V2 would be like an invariant ideal. VH plus 1, etc. is not an invariant ideal. So you have to pick a choice of it. So if you like Iraqi generators or you know, some particular type of generators, you can pick those. We don't think it matters too much which you pick. Okay, and then we set RH to be, again, we're going to do the same Snaith construction. So we're going to take suspension infinity plus of this particular WH minus 1, and we're going to invert a class. We're going to invert, there's a specific generator of this WH minus 1 coming from pi 0 of BP. And it's in dimension 2 times V of H plus 1, which is this suspension there. Okay, so as an example, R1 is KU P localized. So we know what the first one of these looks like, and the question is like, what are the rest of them? So firstly, we check that RH has height h in this sense that I wrote down of Jeremy's. So in particular, LKN of RH is not equal to 0 if n is less than or equal to h, and equals 0 if n is strictly greater than h. So, and RH also, again, it has no completions in it. Its homotopy groups are a Noetherian ring. So I think this is fairly interesting just because it's kind of hard to get, like, you know, if you want a height 3 E infinity ring with Noetherian homotopy groups. You know, there's these topological automorphic forms constructions that exist, but those are very technical and kind of hard to get a good handle on. This is a pretty simple construction, but it gives you something that you know, it's not completed, but it is height 3. Okay, so now, like, in the height 1 case, this was related to P local KU. So now the question is, like, what about in these other cases? Like, they don't seem to have anything to do with E theory because they're not completed. But I mean, of course, they do have this height. So the question is, so if I just pick some E theory, so if I pick gamma, a formal group, height h, say over K, a perfect field, then I get, you know, an E theory EK gamma. And the question is, when are there structured or unstructured ring maps from RH to EK gamma? And this is the main thing that we investigate, is when these orientations could happen. And it seems to have something to do with the sort of arithmetic of gamma. So in particular, you know, like, well, so the first thing we check is that that if you have a map, so there's a map from homotopy ring maps from RH to EK gamma to isomorphisms from the determinant of gamma to GM. Now, so you know, the determinant of gamma is a height 1 formal group no matter what, and all formal groups are equivalent after base change to algebraic closure. So after some, you know, like Galois extension, or I mean, maybe K is I'm thinking about K a finite field, say. And then after some Galois extension, determinant of gamma will be isomorphic. So this is a purely arithmetic condition that to say that there must be an isomorphism between det gamma and GM. So some examples. This is an arithmetic condition. So example, if I look at the formal group with P gamma of X equal to let's look at the formal group where I have this is equal to X to the P squared. Then the determinant of gamma is not isomorphic to GM over FP. But over FP squared, it becomes isomorphic. If I look at P gamma of X is equal to minus X to the P squared over FP, then the determinant of this gamma is isomorphic to GM. Yeah, so I mean, this is why a lot of people prefer the second formal group. You know, so this could come from a supersingular elliptic curve, right? So as an example, if C is a supersingular elliptic curve, then the Weil pairing is an isomorphism from the determinant of C to GM. So, you know, because we get this condition that, you know, we should have a determinant, an isomorphism between the determinant and GM to start looking at trying to build you know, one of these homotopy ring maps or something, you know, so we're going to consider the case where we have a good, you know, a natural isomorphism that comes with a supersingular elliptic curve. So why don't we look at elliptic E theories? Right. So in fact, we checked that in the height 2 case, if gamma has height 2, then there exists a homotopy ring map R2 to EK gamma if and only if det gamma isomorphic to GM. Okay, so now I'm going to state a theorem about elliptic E theories. So in the case of an elliptic E theory, we have a particular isomorphism from det gamma to GM coming from the Weil pairing. And so we're going to investigate just the E infinity maps that restrict to this Weil pairing from the det gamma to GM. So E infinity ring maps that respect this Weil pairing. So I'll clarify that in just a second. But so these are, when P equals 2, they are equivalent as so I guess this is a space. So I should write equivalent to E infinity ring maps from MSU to EKC hat. So C is going to be by the way, a supersingular elliptic curve. I think I just said this out loud. And E over K perfect field, as usual. And then EKC hat associated Moravec elliptic E theory. When P equals 3, it's equivalent to E infinity ring maps from M spin to EKC hat. And when P is greater than 3, it's equivalent to E infinity ring maps from pointed suspension spectrum of some particular Wilson space, EKC hat. Yeah, so this third one is a little bit weird and different because like MSU has no torsion at the prime 2. M spin has no torsion away from 2, but then like the homotopy groups of suspension infinity plus of W14 has all sorts of crap in it. Right, so that's the theorem. I'm just gonna write over here. So in unpublished work of Hahn and I think it's still unpublished work of Hahn and Singer of Jeremy Hahn, Andy Singer. They produce an E infinity map from MSU to TMF13. And so it's possible to post-compose this with E infinity maps from MSU to elliptic E theories at the prime 2. And so this theorem actually does tell us that there are E infinity maps. So that there's at least one E infinity ring map from R2 to an elliptic E theory at the prime 2. I don't think that in these other cases we know that these mapping space, these other, like the infinity ring maps from M spin to EKC hat is non-empty. How am I doing on time? It's been half an hour.
Yep.
Okay. Anyway, so I guess the point of all of this is that right. So in the height 1 case, we actually got KUP. In the height 2 case, we got something we're not really sure what exactly it is. I mean, we have some amount of handle on it, but to some degree we're not really sure. But it is related to the interesting height 2 theories in some good way. I mean, like if you just pick a completely random formal group, it might not have a Bay pairing, and so it could have no maps of any sort. If it's a super thing, if it's an elliptic height 2E theory, then we can use that to produce an E infinity ring map from R2 to it. In the remaining cases at height 2, we don't really know what happens. If it has a Bay pairing, but it's not an elliptic curve, we don't know whether there exists E infinity ring maps. Anyways, our hope would be that these higher height RHs would also have some sort of geometrically interesting E theories that they would tend to orient over rather than, and then they would be less likely to orient like just a random thing. I mean, of course, there's still just this determinate condition, but there's other conditions on a ring we presume to receive maps out of this R3, but we don't really know what's going on with that. So that I think would be interesting to figure out if we could. So, hope is like RH for H greater than 3 also quite prefer geometrically interesting E theories, but no idea. Okay, and I guess in the remaining 15 minutes, I will give a few of the flavor of some of the proofs. Some of these things are really pretty slick and simple. So let me talk about that first theorem that I stated, that if W is a Wilson space, and X in pi 2k of W non-zero, then this ring, say, maybe I'll call it R equal to suspension infinity plus of W with X inverted, has even and torsion-free homotopy and homology. Well, put that in parentheses because it's obvious. And so it's complex orientable. Furthermore, it's also Landweber flat. So I'll give a sense of how this goes. So the idea is that we're going to get a complex orientation by using obstruction theory. So I have my map from S2K to W. I have a map from S2K to CP infinity. And so first I want to extend this. And so this is sort of looking a little bit like the sort of thing that you do with a complex orientation. So to get this extension, I do classical obstruction theory. So the obstruction to performing this extension, these obstructions live in H star plus 1 of suspension 2K plus 2K minus 2 CP infinity with coefficients in pi star of W. And these are all 0. So at least one, I mean, probably a bunch of such extensions exists. We're not going to construct a particular complex orientation. We just show that they exist. So now I have a map from suspension 2K minus 2 CP infinity to W, and its restriction to the 2K skeleton is X. And so now I'm going to invert X. And so I can do, I want a suspension infinity plus here. So let me see. So now let me invert X. And now I can do X inverse. I have the option of multiplying by X inverse on this ring with X inverted. And so this long composite, well, if you restrict it now to the 2K skeleton, right? If I go to the 2K skeleton, then this part is X. And then from here to here, I did X inverse. So the long composite is the unit. Well, the suspension 2K of the unit. So I hope this is clear. This is a complex orientation. Okay, and so now we just have the rest of these claims that it has even and torsion-free homotopy and that it's Landweber flat. So because it's complex oriented, we get a homotopy ring map. Mu to R. And this says that R is a retract of R smash mu. So now to show that the homotopy groups are torsion-free and even, it suffices to know it for the mu homology. Now the mu homology of R is the mu homology of W with this class X inverted. And then by like a T or Hertzsprung spectral sequence or something, you know, W has even normal torsion-free and even normal homology. So it has torsion-free and even mu homology. And so for Landloper flat, it's a bit more involved, but the idea is, I mean, it's not way hard. The idea is that you use the so the BP homology. So the Landloper flatness is about the module structure of BP star of R as a BP star module. And BP star of R is BP star of W with a class inverted, and BP star of W is BP star free. So BP star of R is not necessarily BP star free. In fact, it couldn't be, because we showed that, you know, I said earlier that in some cases R is going to have finite height. And, you know, if BP star of R were BP star free, that would mean that it I mean, heuristically at least looks sort of like to me like a wedge of BPs or some sort of infinite height thing. But the only failure to be BP star free relates to the fact that we inverted this one particular class, and so we can understand. So, you know, ... check it. Okay, so that now it's 9:10. And I'm supposed to, or it's 9:10 in my West Coast time. I'm supposed to end in 5 minutes. Let me see if there's something from the rest of this that can be like very quickly summarized. So I wanted to give some concept of where this isomorphisms from. Right. So the last thing is so where does isomorphisms from det gamma to GM come from? Oops. And let me give some very brief impression of this. Right. So you know, from like Ravenel and Wilson and Hopkins and Lurie, we know that you know that the E theory of an Eilenberg-MacLane space, of a particular Eilenberg-MacLane space, has some relationship to det gamma. So if I have the EK gamma of KZH plus 1, and I take the you know, complete spec or whatever of that stuff, then this is isomorphic as like a you know, formal group scheme to the determinant of gamma. And so RH, we go on by taking suspension infinity plus of a loop space of BPH minus 1 and inverting something. And so what we're going to do is we're going to relate this BPH minus 1 to an Eilenberg-MacLane space. So there are quotient maps. BPH minus 1 to BPH minus 2. So this is like mod out VH minus 1. And this goes down to BP0, and BP0 is just HC. So then I use the going around maps from this. And if I start with suspension H plus 1 HZ, then I get to suspension question mark BP0, BP1, this was BP0 already. And then I keep going, and then I get up to suspension, exactly this number, 2VH minus 1 of BPH minus 1. And so then I hit this thing with suspension infinity plus loops infinity. And this is going to give me some way to relate. So if I hit this with suspension infinity plus of loops infinity, on this side I get suspension infinity plus of k z h plus 1, and then I have some intermediate things, and then on this side I have suspension infinity plus of my Wilson space. And right, so this gives us some foothold that allows us to relate det gamma to WH minus 1. Basically, the idea is that if I have my class here, I have my class X in pi star of this. X is an element of pi star of this. And it turns out that this element X actually is in the image of this map on homotopy. I don't really have enough space at the bottom here. Right, so 2 minutes. Might as well just talk. The X in the homotopy groups here is in the image of a class like B0, the bottom class in the homotopy groups here. I need to K and localize in order for B0 to exist. So after K and localization, then X becomes in the image of a class here. And this class is related to the derivative of formal group homomorphism. So this is sort of imposing isomorphisms. So inverting this imposes isomorphisms from det gamma to GM. If you don't invert this class B0, then homotopy ring maps off of this thing classify just homomorphisms from det gamma to GM. And so anyway, so we chase through this class through this diagram, and so then we can, if we call this thing B0, this ring here was studied by Craig Westerland and Eric Peterson. And anyway, so the point is that if I invert B0 here, then I can call this ring B0, and I get a restriction map. So I just want to say I get a restriction map from some sort of ring maps from RH to EK gamma to ring maps from B0 to EK gamma. And this thing is, if I take either homotopy commutative ring maps or infinity ring maps, this thing is isomorphisms from det gamma to GM. Okay, that's probably good enough. So I guess I'm done.
All right. Thanks for the talk, Hood. Let's see.